This is another video about properties of the Riemann integral. So far, the first video I made was about partitions and an introduction to Riemann sums. The second video you should watch before this one is about the definition of what it means for a function on a closed interval. In that in that video, I worked out an example that utilizes the definition. So in this one, I want to talk about what are some of the properties of the Riemann integral that we're going to end up using later on. Again, we're trying to prove these things. I know that if you're watching this video, it's because you've taken calculus before, and we're assuming that we don't know what the typical rules for antiderivatives and stuff like that are. We're kind of building the foundation for just what is the integral. So what are these properties I want to tell you about? They should look familiar. So if you've got two functions f and g that are Riemann integrable, remember this denotes the set of all Riemann integrable functions over the closed interval from a to b. Then I'm going to tell you about three things. So the first thing, if you've got a real number k, then k times f, that's a perfectly good function, and it's also Riemann integral is what this says. And it also tells me that the Riemann integral of k times f should be equal to just k times the Riemann integral of f. So in other words, if I already know that f is in here, then any multiple of f is in there as well. Similarly, the function f plus g is Riemann integrable over ab. And how do you compute it? The Riemann integral of f plus g is the sum of each of the integrals. And that should look familiar to you as well. Finally, if f is always less than or equal to g for every x in this interval from a to b, then the values of the integral also obey that same inequality. Alright, so what we're going to do is try to prove each of these. Again, it would be some good experience and practice using the epsilon definition of what it means for a function to be Riemann integrable. So the first one we want to talk about, though, is given a tag partition of AB, which we'll denote by P dot here. And so remember that's a collection of subintervals of this AB where they don't overlap except maybe at the endpoints, just kind of one after the other. And then I pick a tag in each subinterval, that's Ti here, and I'm saying I've got n of them, so there's n subintervals in this partition. Then I want to make sure we're all cool with a few things. So number one, the Riemann sum of the function kf over this partition should just be k times the Riemann sum of f over that partition. So why is that true? Well, I know how multiplication and addition work for real numbers. Remember, this scary notation is just this sum here. And so when I am going to add up all terms that look like this, every one of them's got that k. I could just pull the k out front of that sigma. So I could just factor it out. And so that is exactly what we'll do, which of course is this right here. I see I've jumped to the second one already. So the second property that we're going to utilize a little bit later, the Riemann sum of f plus g corresponding to this tag partition p dot is the same thing as the Riemann sum of f plus the Riemann sum of g. And again, this follows from our addition and addition rules of real numbers that I could distribute. And so in particular, this is what the Riemann sum of f plus g looks like. Well, remember, how do you do function addition? That should just be the sum of f of ti plus g of ti. And so if I write that out, which is what I've done here, I've just split that up using my laws of function addition. Now what I could do is I could distribute each of these, so the xi minus 1, distribute it to f and g. And then what do you get? You could split that sum up as well. And so you get this sum plus this sum, which of course is the Riemann sum of f plus the Riemann sum of g. So we're just kind of verifying these things, again, 1 and 2 that I'm going to use. And the last one that it's going to have to do with number 3 up there. So whenever f is less than or equal to g, say on this interval, like the hypotheses of number 3 above that you can still see in green, well then in fact the Riemann sums corresponding to the partition p dot should also obey that same inequality. And so to see that, now in particular, if f's always less than or equal to g, well then f evaluated at each tag is less than or equal to g evaluated at each tag of this partition. And so if you think about, okay, here's the Riemann sum of f corresponding to the partition p dot, well, if we just agreed that f is less than or equal to g of t, what happens when I replace this f by that g of t? Well, I should get this inequality here. And so of course this is the same thing as this inequality right here. So those are the kind of facts that we want to be aware of when we venture to actually proving number 1, 2, and 3. So let's get into that. So the proof of A, well, I guess I called it 1, 2, and 3, so bear with me here. Instead of A, think of that as 1. So we're going to try to prove about the constant multiple. So let's let epsilon be bigger than 0. Now, what do I know? I know that f's a Riemann integrable function, so that means that there exists a delta such that if you give me any tag partition whose norm or mesh, remember that is the length of the longest subinterval in the partition P dot, give me one whose maximum subinterval width is less than delta, then the following should happen. The Riemann sum of f minus the value of the integral should be less than or equal, or just less than, epsilon over k, right? Okay. So remember, for any epsilon, you could find a delta that'll make this stuff work. So I'm saying, okay, I want to make this stuff work for epsilon over absolute value of k, so I want to make delta small enough to make sure that happens. And I know I'm guaranteed to be able to do that because f's Riemann integrable. Think of it that way. And so what I want to think about then is, well, I want to look at this difference right here. Remember, this is the Riemann sum for kf minus k times the integral of f. And I want to show that this thing is less than epsilon. Well, what can I do? By our little fact above, I know that this k should just be able to come outside. And similarly, here's that k that's outside. Well, that's pretty cool. So we should be able to factor k out of the whole thing. And in fact, it should be factoring absolute value of k out of the whole thing. So k is allowed to be negative. But since k is inside these absolute values, again, I hope it makes sense that we're factoring out absolute value of k. And then what did we assume? Well, right above this, I know that this difference, we assume that it is less than epsilon over absolute value of k, so long as this partition, again, has small enough subintervals. And so that's less than this k times epsilon over k, and of course that's epsilon. So that shows that these two things are with epsilon of each other. Therefore, in that case then, we can say that the values of the integrals are the same. I know that his integral, so maybe I should be a little bit more careful. I know that this thing's integral is kf, but if it's within epsilon then of this, then they have to be equal. So if that makes sense how that works. Okay, what else? Let epsilon be bigger than 0. We're going to prove b, which is the summation one. I'll scroll back up very quickly. If you get motion sick, close your eyes. Or really it's number 2 is what I mean. We'll use the sum one, that the Riemann integral can essentially split over a sum is what it's trying to say. And so we'll call that number 2. So again, let's let epsilon be a positive number. And again, I know that f and g are already in the class of Riemann integrable functions, or the set of them, I should say. So what does that mean? Well, for any epsilon, I could find a delta to make sure the difference between the Riemann sum and the integral is less than your epsilon. So we're going to apply that. So I'm going to pick a delta that's bigger than 0, such that whenever I take a tag partition whose norm is less than delta, I have the Riemann sum of f minus the integral of f is less than epsilon over 2. And I'm going to pick delta so small that I also get this, so simultaneously. So that the Riemann sum of g minus the Riemann integral of g is less than epsilon over 2. So I'm going to pick delta so small that both of these things happen simultaneously. And now what we're going to look at is the Riemann sum of f plus g over this partition p dot minus what I think the value of the integral should be. And so what we're going to do is apply the fact that we said above, where we said, hey, this Riemann sum of f plus g, that's the same thing as the Riemann sum of f plus the Riemann sum of g. And again, this was part of our fact above for number 2 here. This is where it's being used. So if I scroll back down here, why is that pretty cool? Well, I'm going to try to group these two together, and then I'm going to try to group these two together. And how am I going to do that? I'm going to split it up with a triangle inequality. So this is less than or equal to this difference plus the absolute value of this difference, which of course we assumed each of these was less than epsilon over 2. And so finally, I finally get that these two things are within epsilon of each other. Therefore, the value of the Riemann integral of f plus g should be this thing right here. That is the limit. That is L. I shouldn't say limit. That is the value, L. Finally, part C, which again should be part 3, which has to do if f and g satisfy an inequality over ab all the time, then so do the integrals. So this one is maybe, it's not tricky, but it's maybe a little bit more tricky than those two. So let's let epsilon be bigger than 0. Again, since f and g are Riemann integral, I can find a delta that is so small so that whenever you give me a tag partition whose norm is less than delta, I should be able to make sure that the Riemann sum is within epsilon over 2 of the integral of f. And simultaneously, I'll pick delta so small that I get this too, that the Riemann sum of g over this tag partition p, and the integral g is less than epsilon over 2 also. So I'm going to pick delta small that both of those happen at the same time. Let's think about this absolute value inequality for a second. Think about college algebra. What's that really say? That's trying to say what's inside is less than, or sorry, bigger than minus epsilon over 2, but less than epsilon over 2. So what we're going to do is we're going to take this and we're going to add it to this side. And we're just going to focus on that piece. When I add that over, the integral of f minus epsilon over 2 is less than the Riemann sum of f. And so I'm going to denote that by star here. We're going to use it in a moment. That's why I'm denoting it by star. And I'm going to apply the same kind of logic with my college algebra, thinking about expanding this absolute value inequality into a compound inequality like I did below. And so if I did expand that, that would be this compound inequality now. And now what we're going to do is we are just going to focus on this half, and we're going to add the integral to the other side with positive epsilon over 2 over there. So that tells me that the Riemann sum is less than epsilon over 2 plus the integral of g. And again, I'm going to need that in a moment. That's double star. So finally, maybe you notice, what did I get to assume? I got to assume that f was less than g over this integral. And so what do I also know? By a little fact above where? Well, when f's less than g, then the Riemann sum of f is less than the Riemann sum of g. And so that's pretty cool, because now I see how to string star and double star together. So the Riemann sum of f is less than or equal to the Riemann sum of g. Therefore, by star and double star, here's what star says. But now this should be less than or equal to the Riemann sum of g. But what do I know about that? I know by double star that is less than epsilon over 2 plus the integral of g. So finally what I'll do is I will focus on these and these. And what I'll do is I'll add this minus epsilon over 2. I'm going to add epsilon over 2 through to both sides. So what do you get then? You get the integral of f is less than the integral of g plus epsilon. Now remember, this holds for any epsilon. Epsilon was arbitrary. Therefore, the integral of f we'll say is less than or equal to the integral of g, which is again what we were after. The last thing I want to tell you about in this section, which again will utilize this idea of the definition of what it means to be Riemann integrable. If you've got a Riemann integrable function, then it has to be bounded on your interval from a to b. And so what this also does, what this result implies, is this kind of big picture idea where, remember, this is a set of, so I've got the set of all functions, and so the Riemann integrable functions on a closed interval AB is just some subset of all functions on AB. So now what we're trying to say is how do these properties compare to each other? And so in this case, if you've got a function that is Riemann integrable, so R integrable, then what we're saying is that implies then it has to be bounded. So what that says then, if you're somebody that's in here, then you're also bounded. So the set of Riemann integrable functions is a subset of all the bounded functions on the interval from a to b. So again, kind of a big picture of what's going on. We're trying to compare these sets of functions on this interval AB to each other. Remember, we had a similar comparison with being continuous and being differentiable. Remember, a differentiable function has to be continuous, but not the other way. So this is a similar idea with that. So how do you prove this? I guess I got to undo all this stuff. Bear with me for a moment. All right, let's get into the proof. So let's say you've got f, it's Riemann integrable on B. And by way of contradiction, that's what that says. Let's suppose that f's unbounded. All right, so we're going to suppose that doesn't happen. So p and not q, classic contradiction. So for convenience here, instead of having this be the integral, I'm just going to denote it by L. So let's think about what it means to say that f's Riemann integrable and how I could use that in the definition with L. And that's what you should be doing if you're trying to prove things or solve some problems in this section of whatever book you're using. So since f's Riemann integrable, what does that tell me? Well, there should exist a delta such that if you give me any tag partition of AB whose norm is less than delta, then we should have the Riemann sum is within 1 of L, right? So in other words, 1 is my epsilon. Remember, if f's in Riemann integrable functions over AB, for every epsilon there should exist a delta. Well, in particular for epsilon equal to 1, I should be able to find 1. So I can definitely find a delta that'll make this happen. What we'll do is we'll rearrange that with the reverse triangle inequality. Remember what that says? That says that this thing is bigger than the difference of the absolute value of each one. And so what do I know? That that's all less than 1. And finally what we'll do is we'll just add this over here. So what I conclude that the Riemann sum, the absolute value of the Riemann sum, is less than absolute value of L plus 1. In other words, the Riemann sum is bounded by absolute value of L plus 1. And we'll call that star, and you can guess I'm going to refer to that a little bit later. Now what we're going to do is we're going to let Q be some other partition of AB, also such that Q has a norm less than delta. Now I haven't told you about any tags in Q yet. Right now it's just a partition. We haven't chosen any tags. But let's talk about, okay, well I've got this function, and so this is a partition of the interval AB. So like we're just splitting the domain of f up into these subintervals here. And what I claim is that since f's unbounded on AB, there's got to be subinterval in this partition Q where absolute value of f is unbounded on that subinterval is what that should say right there. So that's a typo. Change that to unbounded on xk minus 1 xk. So why should that be true? How do I know that there exists subinterval in here so that f's unbounded there, or absolute value of f, whatever you're going to call it? How do I know that? Well, otherwise, this would be bounded on each subinterval of Q. So I should have some real number mi so that this is bounded by that. But then therefore, wait a minute, if it's bounded on each subinterval of Q, then it's bounded on AB. Let me get my highlighter back out. If it's bounded on each subinterval of Q, well, put those together and you get AB. Therefore, your function is bounded on AB by just whatever the biggest bound on each subinterval is. So I know that's wrong. I know that's wrong because my function was assumed to be unbounded. So it can't be the case that f's bounded on all the subintervals of Q. So I hope that that makes sense how we've justified. I've got some bad subinterval where that's where f blows up. Okay, so now what we'll do is we'll choose our tags in Q. So I've got this partition. Now what we're going to do is choose some tags, and then we're going to talk about Riemann integration and stuff like that. So we'll choose the tags in Q in this sneaky way. So I'm just going to let the tag be, say, the right endpoint as long as I is not equal to this k. And what was k again? K is where my function's unbounded. And I'll just let the tag for that integral just be any point, for that interval, sorry, just be any point in that interval. Doesn't matter where it is. So, oh, I'm sorry, I said that wrong. So let me back up a second. As long as your tag's not coming from our bad interval up here when my function's unbounded, I'll just let it be the right endpoint, it looks like. But when we get to where the tag lives in my bad interval, here's how I'm going to pick it. I want to pick that tag so that f of tk times xk minus 1 is larger than absolute value of L plus 1 plus the absolute value of the Riemann sum of all the tags whose index is not k. So in other words, add up all the other things in the Riemann sum except for this kth one. And how do I know I can do that again? I know I can do that because this thing is unbounded. So I could make this as big as I want. So this thing is unbounded on this interval, sorry. So I could, of course, pick a tk that makes sure that f of tk times this number even is still larger than all this junk right here. And you'll see why this junk is special here. This is, again, one of those working backwards kinds of things where I'm kind of, showing you the trick, or I haven't really shown you where it comes from. I'm just telling you that, oh, it's magic, it happens. And so, but anyway, you'll see it in a moment. What can we say then about the Riemann sum of f over this partition, this tag partition Q, where I've picked the tags again in the above manner? Well, let's write out just what that is. It's just this Riemann sum here. But now I want to think about, when I think about a sum, I could write that out individually. It's f of t1 plus x1 minus x0 plus blah, blah, blah. Well, in particular, I could split that into these two pieces. The sum of all the pieces whose index is not k plus the piece whose index is k. So I hope that that makes sense. I've just kind of sneakily rewritten this whole Riemann sum into these two pieces. So I've kind of pulled the kth one off, if you will. But now what I'm going to do is I'm going to employ, again, the reverse triangle inequality, which says that, well, this thing here is bigger than the absolute value of the difference of each absolute value. I guess I should say it that way. So I take the absolute value of each one and take the difference. That's this right here, and I just chose to write this one first. And you'll see why in a minute. What do I know that this is bigger than? So this difference here, we'll look up here. This, move that over, minus that is bigger than absolute value of L plus 1. Now, what just happened? We have, by star and double star, let's go back to star. I should have that no matter what the partition is, as long as the mesh of the norm of the partition is less than delta, I should be able to say that the Riemann sum doesn't get bigger than the absolute value of L plus 1. That should work for any partition whose norm is less than delta. But hey, we just constructed a partition, Q dot, whose norm is less than delta, such that the Riemann sum is bigger than the absolute value of L plus 1. That's the contradiction. Therefore, it must be the case that f is bounded on this interval AB.